Barbara, you can start to record it.
Yes.
Okay. Well, it's my pleasure to introduce again Maria Michalska, who will talk about Lipschitz geometry at infinity. Thank you very much, Maria Michalska, for accepting the invitation. You can start when you are ready.
Oh, yes, I can have my time. Thank you so much. Thank you for the invitation, and I'm really happy to be a part of this day, especially since I'm going to talk about work which has been done between me and my collaborators from here in Brazil. So it's, I think, it's a very fitting topic. So I'm going to now go to my presentation. So I'm not going to see what's happening here. Please, if you have any questions or comments, don't hesitate to try to hail me. You will have to probably do it by voice because I will not see the messages, I suppose. So do bother me. Do bother me. Okay, I'm going to my presentation. I hope it is okay. Oh, yes, yes. Okay, so I'm going to talk about Lipschitz geometry at infinity in a very general sense, but since it's a singularity webinar, we're going to touch upon singularities, of course, too. Okay, so I will focus. Okay, so this is joint work with André Costa and Vincent Grandjean. André was our PhD student, and now he's happily working at the Universidade Estadual here in Ceará. Okay, so I will focus on, in this talk, on global Lipschitz geometry of affine algebraic sets. This is going to be the goal, but the means are going to be very diverse. So this talk is by no means exhaustive. I will focus only on our joint work, and there is a lot of topics which are still open, which are still interesting. Of course, we do not pretend to have closed to close up the topic. Okay, so first of all, the global Lipschitz geometry. So global is, in this context, local at points and at infinity. So if you have the local Lipschitz properties at points and at infinity, if you're doing Lipschitz geometry in the Euclidean plane, in the Euclidean space, then you have all the needed properties. To be honest, this is something to prove, but this is in fact true. So local at points has been extensively studied. So there is a lot of literature on the topic of, especially in recent years, on local Lipschitz geometry of singularities, especially in lower dimensions. So there have been works of, especially that I know of more intimately, let's say, of the group at UFC in Fortaleza. So Lev Birbraira, Alexandre Fernandes, Edson Sampaio, Vincent Grandjean, the PhD students, like André Costa, our PhD students, Sergio Alvarez, Roger Oliveira, Renato Targino. There have been also other very interesting works on, for instance, the polar exploration, which is recently let's say, headed by Pichon, Bellotto, Fantini, Nemeti. So there is a lot about this. Whereas when you look at infinity, the literature is much more modest. So it was initiated with works of Alexandre Fernandes and Edson Sampaio, but the literature is very scarce, and we still want to know and answer a lot of questions at infinity so that we know about global geometry. So this is why I'm saying about the Lipschitz geometry at infinity, because this is the principal part that is the interesting unknown. So we went out with André and Vincent. We set out to explore exactly systematically this property, the Lipschitz properties at infinity. Okay, so to go to the second part of the introduction, well, we're going to talk mostly about Lipschitz. As I said, we're focused on Lipschitz geometry of algebraic sets. So let's say we're going to talk mostly about Lipschitz geometry of sets. And this is like, which Lipschitz geometry of sets? The outer, okay, so we have a set which is embedded inside another set, a metric space. And this metric space has a metric which we'll call the ambient metric. So if I have a subset, I can just restrict the metric and I will have a metric space with the outer metric space structure. Whereas if I take the metric, the ambient metric, and I look at the length of curves, the length metric structure on the space is induced by the ambient metric, but is not the same as the outer. And of course, the standard example is the cusp. So cusp in R2, and we have 2 points. So the inner metric between the 2 points is more or less like t squared. The outer metric, I'm sorry, the distance between them. And here, when I look at the inner distance, meaning inside of the cusp, then it's like 2t, so it's like t. Okay, I'm going to write f is the same, a comparable equivalent to g, if and only if there exists a constant such that we can compare the two with this constant. So here the inner distance is comparable to t, whereas the outer distance is comparable to t squared. So we can see in this example that these two, t and t squared, when t tends to 0, are not comparable. So the cusp, it is true also for the complex cusp. But let's say, let's stick to the blue picture here. So the cusp is an example where the outer and the inner geometry, the Lipschitz geometry of the set, are not the same. And there is a special type of sets which are called Lipschitz normally embedded, Lipschitz normally embedded, LNE, where the outer and inner metric structure are equivalent. And they hold a special place, let's say, in my heart. Okay, so we want to study here both geometries. That's why the Lipschitz normally embedded sets are going to crop up as a test specimen for the relationship between inner and outer geometries. Okay, let's start with the simplest case possible, the algebraic curves. Okay, let's start with not the simplest real algebraic curves. Let's start with the simplest interesting case, the complex algebraic curves. So Renato Targino, in his PhD, which was earlier than the year mentioned here, but this is the year of the publication of the paper, set out to, gave the global outer Lipschitz classification of plane curves. And in his work, he has noticed that what is important at infinity is the arrangement. So the arrangement of the curve with the line at infinity. So we cannot look only at the curve. We have to look at the union of the curve with the line at infinity to ascertain what are the Lipschitz invariants of the curve. So, well, the question of remains, which ones of the curves are going to be Lipschitz normally embedded? And in fact, we have proved that an algebraic curve is Lipschitz normally embedded in the affine space of any dimension. If it has LNE singularities, well, that's obvious because the affine part, so it has to be globally LNE and Cn. If it's, well, LNE, so meaning we have to be able to connect points, so it has to be connected, and has LNE singularities, so locally it is LNE at points. Of course, I have not mentioned this, but I think we do know that if we have a smooth manifold, it is Lipschitz normally embedded. So the difference between the outer and the inner matrix structure can only arise in singular points. So this is why we're talking about singularities here. So algebraic curve is Ln in Cn if it's locally Ln and intersects the hyperplane at infinity at exactly the degree of C distinct points. So it means that it intersects the hyperplane at infinity. The hyperplane at infinity intersects it transversely at smooth points. So this is Ln, and this is if and only if. So the curve has to have at every point at infinity, it has to have this property. So the characterization is very simple. In fact, what is kind of surprising, especially knowing the works of Pham and Tessier, is that you cannot reduce, the classification of Lipschitz normally embedded curves and the Lipschitz and thus the Lipschitz classification of curves cannot be made to a Lipschitz classification in the complex plane. There, in any dimension, you can find a curve which does not have a representative on the plane, which is contrary to the local case. So this is in fact something of interest on itself. Okay, so let's go to. Okay, so let's go here. So locally at a point, one can even prove, and it is known already by various results. Now I do not remember who was the first to prove it, but it's a well-known fact that for a curve to be locally Ln at a point, it has to be it's Ln if and only if transverse. It's a transverse intersection, pairwise intersection, not intersection to, but union of transversely intersected smooth components when we think about a germ. So this is in fact if and only if, and this is Ln for a curve. Whereas, okay, let's look at infinity. This arrangement is not going to be Ln. So it is an Ln arrangement that yields a non-Ln curve. Let's look for a moment at, well, why is it so and why it's almost obvious. Well, this is not the only case that you need to consider to prove the previous theorem, but this is the main point I want to make. So let's look at this arrangement and why it's not Ln. So here, the affine picture. So let's draw the coordinates. And what happens to the curve? Oof. What happens to the curve? Well, here we have two. Well, the tangent cone is here. We have lines which intersect at the same point at the line of infinity, but are not the same lines. So it means that they are being like this in the affine picture. So now the curve goes somehow like this. It's supposed to be connected, so I can connect it. So let's look at distances of points on this curve. So here, let's say, look at xn, yn. So I'm saying that this curve is not going to be Ln. Let's look at the outer distance. The outer distance is like a constant. Let's say in the real picture, it's absolutely like this. So here I have this sequence that has the outer distance like a constant. But if I want to take the inner distance, I have to go all the way down. So when these points tend to infinity, this length of this curve needs to go to infinity. So the inner distance between these 2 points tends to infinity. So we can see that these two are not comparable, the outer and the inner distance, and that ends the proof. This is not an LNE set. So what does it says? Well, it says, in fact, that projective closure does not preserve Lipschitz geometry. Because, well, we can have something locally LNE which is not LNE. So either it breaks the inner Lipschitz geometry, or it breaks the outer Lipschitz geometry, or it breaks the relation between the inner and the outer metric. So unfortunately, we cannot look at the most popular and most natural compactification of the Euclidean plane when it comes to algebraic sets. Okay, so what can we do about this? There is a very nice tool, because if you work in real geometry, you do that pretty often, and it is the inversion. In fact, with Vincent, we have, I've used it for to localize already multiple, let's say, the degree, the poles at infinity of polynomials, to localize them as points. And we've used it with Vincent, for instance, to make regularization at infinity of polynomial mappings, to treat them as rational mappings. In the real world, it works very nicely because the sphere is an algebraic variety. So the inversion is just a simple mapping, x to x over the norm square. So the norm square is just in the reals, so it's real. And the norm square is just a polynomial. So it works pretty well with the real structure. What else does it have? Okay, so here I have a picture. It takes 0 to infinity. Of course, you define it on Rn without 0, and then you can extend it from 0 to infinity. If it depends. Okay, and it exchanges something. If something has a radius 1 over r, it takes you to a sphere of radius r, and vice versa. If something is of radius r, it takes you to the radius 1 over r. So it's really an inversion. It flips the one-point compactification of the real plane. Well, it inverses the reals. It commutes nicely with stereographic projections. So if you inverse the sphere and put, if you inverse the real plane, do the stereographic, well, not the real, the Euclidean space, you put the opposite of the stereographic projection, and then you project, then it's like the projection of from the South Pole. So from North Pole, inversion, and it's the same as from the South Pole. So in this way, it commutes nicely. What's, let's say, the most important remark is that the inversion, well, the inverse of inversion is the inversion itself. Well, I said it commutes in a way with stereographic projections, and well, unfortunately, beware, does not respect complex algebraic structure. You have to beware of what happens to a complex set. Well, just making an inversion to the complex set, it loses the algebraicity of the set, complex algebraicity of the set a priori. Okay, so let's look how to use the inversion. Okay, maybe. So if I take a let's say I will take a homogeneous polynomial, and I look at the inversion of f with the inversion. So it is the same as I of f of x over x squared. So since I took f being homogeneous is like the inversion of 1 over x to here, I end up with fx. So after doing the second inversion, which I'm not going to compute because I'm lazy, but I end up with something, well, this is homogeneous map, of something homogeneous of degree f. So in principle, this is why you can use it to study polynomials, but if f is linear, then if I take I, f, I, then this I end up, so the inversion of f, so it means that if f is, so this takes 0 to infinity, this takes 0 to infinity. So if I had f, well, linear doesn't matter, but if I have f from Rn 0 to Rn 0, then the inversion makes it such that I can treat this as a term of a mapping near infinity, and vice versa. So this is why we're going to use this. So if I have f linear, then this I expect to be linear as well. It's kind of obvious-ish. Okay, so here I have this remark. So this is the remark I just made. So if I have something linear, then it's the inversion on f on inversion is something linear. And on the other hand, if I have a bi-Lipschitz map near 0, it's almost linear because, well, in particular, let's say f of 0 equals 0, then this is exactly what I get. I have f of x minus f of 0 is comparable because it's supposed to be bi-Lipschitz. So it's, okay, L is going to be big or small. It's comparable to a norm of x. So it's almost linear. So what do we expect? We expect, in fact, that it will happen that the inversion, so we expect that the inversion of the bi-Lipschitz map is still going to be bi-Lipschitz, like in the linear case. And in fact, this is the case. So Vincent with his PhD student, Roger, have proved that if we have an outer bi-Lipschitz map near 0 between two sets, one is in Rn and the other in Rm, the ambient dimension doesn't really matter, but well, the f is a homeomorphism between x and y. Then the inversion of f, which I will call I. So taking the right and the left composition with the inversion of f, is going to be outer bi-Lipschitz near infinity. So if we have outer bi-Lipschitz, then we have outer bi-Lipschitz. So in fact, our intuition was absolutely correct. And there is absolutely no assumptions on regularity of f. This is true. This is just a homeomorphism. The sets are whatever closed sets. Well, I suppose it's I suppose, let's say, closed sets only. So regularity of f, there is no assumption on it. So they are whatever type of sets. So now we have outer bi-Lipschitz property. So let's look at the inner bi-Lipschitz. And in fact, it's even easier to prove that if we have something inner bi-Lipschitz near 0, then f is inner bi-Lipschitz near infinity. The inverse of f is inner bi-Lipschitz near infinity. But we need to have a tame condition. Tame condition on the sets. The inverse of this theorem holds under reasonably obvious assumptions also. And this same condition here, again, there is no, except for these same conditions here, there is no assumption on regularity of F on the sets, nothing whatsoever. And these same conditions here, in fact, they are satisfied by all definable sets. It just stems from the regular Lipschitz cell, so L cell decomposition of a set, because here we only look at the distance from the origin. We do not look at the distance between points. So let's look at the cusp. So if I take the origin of the cusp, in fact, the inner metric between x and 0 in the cusp is in fact comparable with just the norm of x. So a cusp which is not LNE by any means has this property. And in fact, this property is satisfied by all definable sets. You can think semi-algebraic. So you can think about analytic singularities, globally analytic sets, sub-analytic sets, semi-algebraic sets, algebraic sets. It's all going to work. This condition is going to work for them. So in all the cases we are interested in, we have that inner bi-Lipschitz mappings. After inversion, they give inner bi-Lipschitz mappings near infinity, so from 0 to infinity. Do I want to say something more? Okay, so yeah, well, these results, if somebody wants to check out, it's let's say originally the compositions into LNE sets are by Kurtyka and Paruszyński, and another again a Polish mathematician that I forgot the name at the moment. So they initiated it in the 80s even, or late 80s, early 90s. The papers were. I don't remember, so maybe I'm going to write 90s and don't remember exactly. I'm sorry. If anybody is wondering, I can check for you very easily. Just got out of my mind for the moment. Okay. But I need to be going, and so, okay, we already know that what we have learned is inversion preserves outer bi-Lipschitz equivalence, inner bi-Lipschitz equivalence, and, well, the third component missing is, well, relationship. So this is relationship between the inner and outer metric. One can find a formula, but let's say there is a pretty good Slackman's test of the relationship between the inner and the outer metric, and these are the Lipschitz normally embedded sets. And so, in fact, we have proved that, yes, the third component here, so this one, and this one in a moment, yes, for a definable set is LNE at 0, if and only if its inversion is LNE at infinity. So under, let's say, the condition for the set, so that we can say we don't have problems at infinity, is that if I remove 0, it will not disconnect the germ of the set at 0. Because otherwise there is going to be problems. But apart from this mild condition, this is exactly what happens. So, in fact, the corollary is that the
you want the set to be closed or not?
Yeah, well, here we work. Okay, I should say I work with closed sets out of convenience. So I wasn't even thinking about adding this. Yeah, it's only closed sets With open set, well, with non-closed sets, there is some trouble. I'm not going to go into it at all. So closed set. Do remember that if you have a set which is ln, then the closure is going to be ln, vice versa is not true. Okay, so the corollary is a closed definable set is ln in Rn if and only if its one-point compactification is ln in the sphere. So in fact, what happens is I just have a sphere, I do the one-point compactification of the set, and I look at the set as a compact subset of the sphere, and now I have all the possible criteria that have been already evolved for the local case. So as long as they are defined.
Any one-point compactification, right?
Huh?
You mean any one-point compactification?
Yes, of course. Well, because there is only one-point compactification.
No.
Well,
No.
Topologically, yes. Well, topologically there is only one, but yes, metrically there might be different ones. But we are working here. I think this is pretty obvious from the context here that we are working with the inversion. So we are working with any metric on the sphere which is equivalent to the standard embedded metric on the sphere. That's so. So whenever a metric on a sphere is equivalent, this is the same. So, well, how many metric structures on a sphere do you have? This is a question for a metric geometer. But as far as I understand, when you look at this as a manifold, well, there are only certain dimensions of the sphere that you have. You can end up with non-equivalent metrics.
If you talk about one-point compactification of R to the n, you are right. But you are talking about one-point compactification of your set X, right?
Yeah. Okay, I know what you mean. Okay, now I understand what you meant.
Because this, and that is why.
No, it's an embedded compactification. So it's when I say it's one-point compactification, I mean it's X the pair. The pair. I'm sorry, this is not the pair that I was. I now understand the meaning of your question. Okay, so I have the pair and I one-point compactify the pair. So it's naturally, so I have, because if I want to preserve the Lipschitz normal embedding property of the set, I need to preserve the embedding. So I cannot compactify X just without any. I want to study here the Lipschitz geometry of a set embedded in a space. So I want to preserve the properties of the set with respect to the embedding. So it's kind of, let's say, in my mind, it was very natural to think already about the one-point compactification, the embedded one-point compactification. So I was answering a different question in some sense. Okay. So 1 point, so that I have, let's say, this one-point compactification.
Okay.
Thank you for the question, because I hear that I'm being listened to. Thank you so much. So plus the point and the Sn, which is Rn plus the point. Well, let's say it's the infinity, p equal to infinity. I don't want to erase it now. Okay, so this is the one-point compactification. And this is true that it's good that we stop here for a moment, because to all the audience here, there is a very different metric. In Rn, well, Rn is not compact, the sphere is compact. The metric is very different. One arises through a transformation of the other, but it is not, let's say, self-evident that that the relationship is going to stay the same. So let's say this is not, a trivial thing. Well, it's not hard, but it's not trivial. This is a very nice lemma that allows us to use, as I was saying, to use all the definable criteria that was already done for sets locally at 0, to use it at infinity. So I'm going to give us corollaries here. So there is a theorem of Rodrigo Mendes et Sampaio, which was generalized with a very nice different proof by Nguyen, that the connected germ at infinity is ln if its link is ln with a constant independent radius. So I'm putting here already at infinity. So this is the contribution, because their theorem is at a point. We can do it at infinity. So it's pretty evident, for instance, that obviously from this you get that if F is homogeneous, then the zero set in Cn is ln if and only if it has globally ln, it has ln link, for instance. Well, because it's just a cone, so it's going to be independent on the radius. So a very simple example here. Another corollary is that we have a theorem of Alexandre Fernandez and Edson Sampaio about cones, tangent cones of sets. So a cone at infinity. So now at infinity of an ln set is ln, whereas normally it's at a point. And we can use all other criteria as long as they are definable, because algebraic ones can break because of the inversion, or let's say you will have to try to rewrite this criteria. It's not going to travel so evidently, because here you don't have anything to prove. It's just, this is for definable sets. I didn't write here, I think. So this is definable sets. Yeah, I didn't write it here. So these are true for definable sets. And so if something is for definable sets, you just remove at the point, put at infinity, and that's it. Okay, so what I wanted to... So, yeah, I'm talking about Lipschitz normally embedded sets. And as I said, they're pretty good Lackmus tests for testing of Lipschitz properties with respect to different operations on the space. But, well, what about all the other sets? Well, in fact, there is a very nice theorem that started up with the Lipschitz normally embedded name, and it's the theorem of Birbrajew-Mostowski. So, in fact, this paper gives rise to the name Lipschitz normally embedded. So the paper gives the condition for compact sets, and using the aforementioned results, it's very easy to state it now for non-compact definable sets. So any closed definable set is inner by Lipschitz equivalent to an Lipschitz normally embedded set. So if I have any closed definable set, and it doesn't matter whether it's compact or not, by inner by Lipschitz equivalence, I can just study its ln model. So what it gives me is that the inner Lipschitz classification of definable sets is the Lipschitz, well, the inner or outer, because it doesn't matter, classifications of ln definable sets. So it's a very nice tool, because here you can use methods from inner and outer geometry, because Lipschitz normally embedded sets, they have the same structure, so it doesn't matter whether you look at the inner or outer classifications. And of course, the ln definable sets are a smaller class. So it's much easier also to try to classify via Lipschitz equivalence ln definable sets. On the other hand, if you have a Lipschitz classification of ln definable sets, so for instance, if you look at the classification of definable curves, which is not the same as Lipschitz classification of algebraic curves. So if you have a Lipschitz classifications of definable curves, of ln definable curves, then it gives rise to inner Lipschitz classifications of all definable curves. Of course, here I'm saying closed, because otherwise when you take out pieces, it's going to be messy, but then you can classify the pieces and the relationship, but I suppose it's going to be messier. I have not even thought about this. So okay, so this is why I wanted to do some LNE sets, but still here, as I said, like if I have something for definable sets, it doesn't mean I have the properties for algebraic sets. So again, like where do we, I said the goal was to go to algebraic sets, and I'm looking at the time. I'm going to be on time, maybe even be before time. So what I wanted to talk about, I'm just going to look. Okay, so let's go back to the algebraic sets. So before we go back to algebraic sets, let's make another detour. So we had some theorems that had absolutely no assumptions and regularity. Then we had some tame condition, which led us into definable category. Now let's go, well, there are of course tons of results on metric geometry. So for instance, if the LNE constant is smaller than pi over 2, then the set needs to be simply connected, for instance. So there is a lot of results already with LNE sets, but let's try to go back now to one, let's say we go back to the algebraic sets, but we're going to make a detour once again, let's say to the smooth category. And so let's look at the very classical thing, which are conical singularities. So there are papers by Chigor. There is a lot of literature about conical singularities, and not only conical singularities at a point, which is like classical physics applied questions, but also about conical behavior at infinity of manifolds, also a classical problem. I'm not going to go into strict definitions here. I'm just going to present it. Well, it's almost strict, but hand wavy. Okay, so let's start with, we know about blowups, but let's talk about the real counterpart, the spherical blowup at 0. So well, this blowup goes this way. So let's say we start here with Rn, and I have a point, and I write it in the spherical coordinates. So it's the unit vector from the sphere times something, well, times the radius, which is something non-negative. And I take this point to be represented on the tube, positive times the sphere. So it's just a point that, well, it's just R times U. So RU goes to RU. So it substitutes the origin with the sphere, and the spherical blowup at 0, well, you can nicely inverse it and have a spherical blowup at infinity. And then this is going to be natural compactification of the reals with the sphere at infinity. So everything is very, very classical. So we say that a set has a conical singularity at 0. I'm going to use the embedded definition here for the convenience. If it's strict transform, so again, so if I have a set X here, the strict transform, although it's a different blowup, but again, it's the pre-image closure under the pre-image. So the strict transform of X is a submanifold near the boundary. So the boundary is here, the sphere, well, at infinity, or the sphere substituted for 0, and meets it transversely. So it's a P submanifold of the tube, to be honest. So, and again, the same is going to be true at infinity. In some sense, starting from definitions, you need to prove it, but you can think about conical singularity at infinity in exactly the same way that if I do the spherical blow-up at infinity, I will get the strict transform as a submanifold near the boundary. But again, at infinity, you have this problem. What is the metric? And again, to circumvent this problem, we use inversion to think about. So there are some things to prove, but when you think about just using inversion, it's gonna be good, because I don't have time. Okay, so why do I talk about this? Okay, so this is a very natural concept. I wanted to define it because it's very simple. So let's say we got this here. We got into differential geometry for a moment, and let's go to the algebraic sets. So a generic algebraic set has conical singularities at infinity. So it's real or complex. The conical singularities at infinity are real. So let's say, again, this does not agree well with the complex algebraic structure of the set. But you can prove it has conical singularities at infinity. And, well, this is pretty simple from the way I have presented it. Conical singularity at infinity is ln, if and only if its inversion is ln at 0. So if I have a conical singularity at infinity, ln.
I'm sorry, just I'm not sure what do you mean by generic.
Well, it means that there exists. Okay, so this is a good question. That's why, let's say, we have spent some time in the paper explaining exactly what it is. So generic, we will mean looking at the algebraic affine sets as 0 sets of polynomials. So when I have polynomials f1, fn, and they give me a 0, then the ideal generated is the ideal giving me the algebraic set. Then I say that, so I will fix, so an algebraic set is the same as the 0 set of a mapping. So this is how I treat algebraic sets. And now the generic is going to be whenever I fix the, okay, so let's say this algebraic set is going to be ambient dimension. So ambient dimension n, and I fix the number of polynomials equal k, and I fix their maximum, their max degree. So I have a very nice finite dimensional space. Then there exists a Zariski open dense set V in the space of R x1 xn of degree, let's say, of degree at most d times k times, so of mappings xn such that, okay,
such that the germ of infinity is ln e, right?
Yeah. So well,
in the same sense as if you take a germ in a set, then for generic algebraic set, a germ is non-singular, right?
For instance, yes. Yes.
All singularity theory is non-generic in general, and then all non-conical singularities are not generic in this sense. Okay.
Yeah. In fact, well, let's say this is just so there exists.
I understood.
Yeah, because in fact, what happens here, you can somehow iterate from something which is generic, meaning because let's say for other people, do remember that if something is locally LNE at every point, because smooth, so like a parabola, it doesn't mean that it is LNE in R2.
Yes,
because
parabola is not generic in this sense.
Yeah, exactly, because parabola is not generic.
Neither parabola, nor cubic parabola, anything is non-generic.
Yeah, but I just wanted to say that even if we have generic smooth things, it doesn't mean that they are necessarily LNE. That was only for other people to say.
No, but I just you answered exactly. You answered the question. Okay, thank you.
Okay. So, okay, thank you. Thank you for your questions, to be honest, because I feel heard. I feel heard. I did not lose my connection here. Okay, so in fact, the way we go around proving this is that we prove that in fact the generic algebraic set has conical singularities at infinity. Conical singularity at infinity is LNE if and only if it's LNE after inversion, basically, because that's what happens somehow. And the conical singularity at 0 is LNE. So going back, we have conical singularities. Maybe I'm going to change the color. Conical singularity is LNE. So the conical singularity at infinity is LNE. So a generic algebraic set has conical singularities at infinity. And so it is LNE at infinity. So okay, I'm going to go to the other slide. So a generic algebraic set is LNE. So in some sense, we can also iterate in a moment. Generic singularity of multiplicity K is LNE because, well, let's say an example of conical singularities are going to be non-degenerate singularities with smooth link. So it's going to be of also LNE. So in principle, we can, so in particular, an isolated singularity. Sorry, I started. So an ISIS is LNE. I'm sorry, I just isolated complete intersection. I have too many eyes. Complete intersection singularity is going to be LNE because ISIS are generic among the singularities, how we treat them. Again, genericity is again.
What about complex curves?
What do you mean? What about convex curves?
Complex curves.
Complex curves.
Complex plane curves. So
well, so it's already it's already known that the complex curve generically is an LNE curve because even from the previous result, whenever you have
so it means that is it generically non-singular, right? Because it's LNE or even only.
No, it's even because here I gave exactly multiplicity K. So it's like you have a multiplicity and among with such multiplicity, so it's singular. Although in the case of curves,
multiplicity already means that it is not LNE, right? Just according to the theorem of Renato, if it is singular, it's not LNE.
What is not LNE?
It's infinity. It cannot be because multiplicity, they have this kind of R.
Yes, but exactly like already from the previous theorem of myself, Vincent, and André, the theorem said that the intersection. So I have a, let's say, in the projective plane. Let's take a projective plane and let's take any curve with any type of singularities. They might be much worse. So The theorem says that if I intersect it with the line,
Yeah.
such that it intersects at exactly degree of the curve, distinct points. So it intersects transversely and smooth points of the curve. Then the affine trace, so if I treat this line as a line at infinity, then the affine trace is ln if and only if the projective curve was ln. So if and only if the singularities here were already ln, but in general, like affine trace is ln at infinity if and only if I have intersected with the line at infinity in a transverse way, in a generic transverse way. So it already showed that among complex curves, you already have this genericity property. It was already there.
So that, right.
And in fact, it also somehow
means generic. I'm sorry. That it means generic means smooth, but generic means smooth for the complex.
No. Generic does not necessarily mean smooth. Now, okay. So in this context,
any singularity of a complex curve is ln. There are no ln, but only if you have transversal intersection, right?
Yes.
I see.
Yes. So this is why I made the picture to try to say, like, in this context, generic will refer to the fact that if I have any ln projective curve, if I embed it, well, if I take out a collinear deck C points out of this curve, then it's going to be ln embedded into the affine plane.
Okay.
So this is because, in fact, there is also, let's say, we were pretty cautious to write in the paper this. Let's say during the talk, I'm using this pretty freely, but in the paper we were pretty cautious to be precise what genericity means, because sometimes we do really mean that generic intersection with the hyperplane at infinity. So it said, so here the generic intersection with the line at infinity gives rise to an ln curve. So in exactly like the question here, it's like we can make an iteration of this exactly in the same way, because what we prove is that the transverse intersection with the hyperplane at infinity of an algebraic set is going to be ln. So in fact, if I have isolated, well, I'm pretty sure that if I have a, let's say corollary here, the different type of genericity is going to be if I have if X is a projective. So maybe I'm going to say it's already embedded, not projective, abstract projective, but embedded in the projective space with ln isolated singularities. So like a minimal surface by Ampichon and Helge Pedersen and Neumann, for instance. Then general affine trace in Cn is ln. So by a general affine trace, I mean exactly what happens when I take a hyperplane intersected with X and treat the hyperplane as hyperplane at infinity and the complement of X as an affine complex algebraic set in Cn. So for instance, we have this iterative corollary. I think I have run out of my time. So I thank you for your attention.